Hey, math moment makers. This week we interview the great James Tanton, author, curriculum writer, speaker, global math project organizer, creator of Exploding Dots, and spreader of joyous mathematics. We bet that you'll find yourself smiling as you listen to James' enthusiasm for mathematics and how we can help make math moments that matter for our students.
We were so pumped to have James on the podcast because his enthusiasm for mathematics is so contagious, and we know you'd love to listen to his journey and message. So let's do this. Cue the music.
Welcome to the Making Math Moments That Matter podcast. I'm Kyle Pierce.
And I'm John Orr. We are two math teachers who, together,
with you, the community of educators worldwide, want to build and deliver math lessons that spark engagement,
fuel learning,
and ignite teacher action. Welcome to episode 6, Looking for Joy in Mathematics, an interview with James Tanton. Are you ready, John?
Let's dive in, buddy. But before we do, we want to thank our sponsor, Whitebook. Whitebook provides great dry erase tools for you to use in your classroom. Stay tuned after the show for a special deal from Whitebook. Let's not keep you waiting any longer. Here's James Tanton.
All right, welcome James Tanton to the podcast. How are you doing today, sir?
I'm doing spectacularly well. Life is mighty good. How are you guys?
We are fantastic. This is a unusual episode because John and I are actually in the same room today, which is kind of nice.
Kyle, you let the cat out of the bag.
Yeah, people might have assumed that we were always together when we were recording this, but not the case.
So there's a question. Are you in the same room when you're video recording, or are you doing clever school?
Oh, yes. You know what? Sometimes I think actually we should probably play with that idea a little bit. 2 different green screen rooms here and there. Usually when we're in the same frame, we're together. But you never know. Sometimes we've got to do some edits on the fly to find that same shirt and go from there.
Plaid shirt.
Love it.
Well, listen, James, we want, for those who don't know you, although you are quite a global influencer in the mathematics or math education field, tell us a little bit more about yourself. Like, what's your teaching story and I guess your math journey?
Oh, gosh, my math journey, my teaching stories. How long do we have for this podcast? I can go for days.
As long as you need, my friend.
Let's see. All right, so even for your audience, I probably have an accent. So probably people realize I'm not from North America. I'm not from the US, even though I live in Phoenix now. So I grew up in Australia, grew up in Adelaide, Australia, born 52 years ago, quite a while ago. And let's see, so my mathematics story. It did not start with joy, the mathematics one. So I went through a school system back in Australia, back in the 60s, 70s. It was very much procedural rote doing. The Anglophilic system, that is, my job as a student was just to not ask questions, just to memorize and to do. And there were a couple of times I tested that system and got knocked back big time. One formative moment for me as a kid in the classroom was grade 9. So that was the year we were learning the Pythagorean theorem, which seems late to grades today, but that's how it was back then. And it was a big public school, 37 kids in the room. And our teacher asked us each to draw a right triangle. In fact, draw 3 right triangles on our pages, get out our rulers and compasses and do that, measure the 3 side lengths, and work out a squared, work out b squared, work out c squared. And of course, the 2 legs were called a and b, and the hypotenuse had to be called c, had to be that order, and see that a squared plus b squared equals c squared. And I had 2 questions about that. One, I realized that no one can actually draw perfectly and measure perfect. So I realized no one was actually going to actually see a squared plus b squared equals c squared due to human error and all the rest. But I let that one slide. But I did raise my hand to Mr. Phillips at the time and said, "Excuse me, Mr. Phillips, how do we know this wasn't just a coincidence 111 times in a row? There's, maybe, we just did 111 examples. Maybe it's just by luck it all worked out each time." And his response to me was really, really, it spurred me on. His response was, "Go back and draw another 3 triangles." So basically the message I got was, I'm not going to be told why this is true. My job is to figure it out on my own.
Wow.
And I stuck with, and that stayed with me for years. And I think I was doing some reading on the side and all the rest. And I figured out some proofs of the Pythagorean theorem by then. But I realized I'm in a system that's not going to actually teach me what's going on, just teach me how to do it. And my job is to perform. So that actually spurred me on. So it actually kind of made me angry. Rather than shut me down, which I'm sure it shuts many kids down, kind of it quietly spurred me on. So I did go back and fall in love with mathematics at the university level, which was really about all the why and what if questions, all the things I was naturally asked as a kid and wasn't allowed to ask for basically 12 years of my schooling. So it spurred me to really wonder about why does math work the way they do. And I remember taking an abstract algebra class in particular, which is all about arithmetic. What are the axioms of arithmetic? What makes it work the way it does? And I thought, oh my goodness, I'm finally home. This is what math is. Why couldn't someone tell me this all along? And I knew I was a mathematician. So I basically fell in love with math and just went through as far as I could, all the way through undergraduate. My first degree was actually in theoretical physics. It took me a couple of years to realize that math was actually my thing. But then in Australia, you get to do something called an honours degree, and I switched over to my mathematics and my honours degree for my fourth year of uni. And then went on to a PhD, and that's what brought me to the US back in 1988. So I got a PhD in mathematics at Princeton, in that whole sort of, high-powered research world. But I've always had a strong passion for sharing the beauty and the joy of mathematics, and primarily through teaching. So rather than stay in the high-powered research world, I became a professor at the liberal arts college environment for my university career and loved it. So I wanted a strong focus on teaching and the research. And then life took me around up and down the east coast of America. And I eventually fell into doing a lot of PD work, professional development work for teachers in the Boston area, which made me start looking at the curriculum again, the school curriculum. And I looked at this, and this is the late 90s in the US, and I have to say I was dumbfounded and shocked and deeply saddened because I basically saw the same memorized, procedural, and just do type of joyless curriculum that I went through back some 20, 30 years ago in Australia, on a different continent. And it was still just do, don't understand, just do. And it made me outraged. And I kind of decided then, rather than be one of these professors that complains about what high school teachers do, because professors always complain about high school teachers. And by the way, I know high school teachers always complain about middle school teachers, and it goes all the way down. It's just silly. Just silly. Just don't complain. Just do something about it. I decided to be honest and become a high school teacher. I wanted to understand the system and really understand what are the barriers, the difficulties, the frustrations, the limitations that actually make it hard to turn things around. And I wanted to honestly see, can I attend to this high school curriculum and do so that teaches the thinking and the joy of mathematics and still get the kids to pass the exam? So I became a high school teacher for 10 years. So basically, I'm one of these strange creatures that sort of kind of let the team down at the Princeton University level where, high-powered research, and what I'm doing is becoming a high school teacher. And I really, and I know I said it with a funny sort of disdain in my voice there, because that's kind of what I felt back then, like 20 years ago, that it's that high school teaching was looked down upon. I felt it in the tertiary world, which is silly and morally wrong, because education at all levels, whatever level it is absolutely vital, important, and essential. Be it the graduate school level, great. Be it the kindergarten level, fabulous. Be it high school level, fabulous. It's all equally important.
Wow, yeah.
So that sort of made me angry. But I did that. So I became a high school teacher, and now my life is just basically, I'm not actually in the classroom right now, which is kind of strange and sad to some degree. But I'm also in this wonderful position where I get to go and visit people all across the globe now, go visit schools and classrooms and colleges and talk about how can we make mathematics joyous and meaningful and relevant and human to one and all, no matter which curriculum you're working with, no matter how enlightened or unenlightened it is. It's still a challenge. What's the human story? So I feel very privileged and honored to be having spent 20 years of my life trying to think about that on my personal level and then trying to share whatever random ideas I've had and talk to other people about. Let's just bring the joy back to mathematics. So that's my career in a nutshell. So that was probably longer answer than you wanted, but that was beautiful. There was my monologue of who I, James Tanton, am. Just a guy who's just passionate about mathematics, how it's really a human, creative, organic enterprise. And I feel like I'm a man on a mission to try to do whatever I can personally to share that with one and all. Be it the teachers, be it the administrators, be it the parents, be it the kiddos themselves, everyone, literally everyone.
Well, I think something like that, early on, I wrote myself a note here. I wanted to comment on it, but even going back to your experience in the classroom and thinking of, how curious you were despite the way the curriculum was being shared with you. I'm pretty sure John agrees with me on this. Like, I wasn't even thinking those questions because I had my curiosity, like I like to call it, like, sucked out of me really early on. Like, I was not a curious child anymore. And I'll be honest, I didn't even think I was very creative. And sometimes, and I need to take responsibility for that as well.
Mhm.
But at the end of the day, I think I was just so used to going through the memorizing and the steps and the procedures. I almost got to the point where I didn't want to know why anymore, because I realized that for me, memorization was so much easier. And I just love how you weren't satisfied with that, even as a younger student. And, you obviously led that path all the way to, becoming, getting your doctorate in mathematics. I love your idea that you went back into secondary to teach. I think a lot of secondary teachers who are listening would probably, be really happy to hear that, wow, a professor from university came back to do the job that we're doing. And sometimes I feel the same about elementary teachers, feeling the same about, that same feeling like of the secondary teachers not appreciating the work that they do. And I've had the opportunity to go from secondary into elementary over the past couple of years. So I feel like, although different, very similar situations there, where I've just been fascinated with how awesome the mathematics is at the younger early years, with kindergarten kids and kids in primary, just learning how to count, and how important that those early stages are in order for students to really understand the mathematics that we're trying to help them understand and do so in a joyous way, like you've articulated.
And
here.
here's the thing, all levels of mathematics are actually incredibly intellectually rich and profoundly nuanced and deep. So one of the pieces of flack I kept getting from my colleagues at the university level was, aren't you just bored out of your brain talking about, K through 12 math? And the answer is no, because the deeper you think about things, the more you realize how deep they are. Even the act of counting is fundamentally subtle and nuanced. There's so much intellectual richness to probe and explore there. So on the, you might be working with very young kids that aren't going to experience that themselves, but as an adult, you've got depth of richness of understanding can sustain you for many, many years at all levels of education. The fact that that we like to believe that multiplication is commutative. So I'll use the fancy language we'll never use with small kids, but why should 3 times 4 philosophically give you the same answer as 4 times 3? Yes, I know the answer is 12 in both cases, but I want the philosophical reason, without actually having to say 12. And it becomes one of these epiphanies when you realize, oh, if I take 3 groups of 4, how we understand multiplication on the counting numbers level, and arrange them in a symmetrical, beautiful, pleasing pattern of a rectangle, and then look at it 2 different perspectives, then you see, suddenly it leaps out to you, oh, 3 groups of 4, 3 rows of 4 is the same as 4 columns of 3, 4 groups of 3. Philosophically, it's the same. That's an aha moment when you realize our beliefs arithmetic based on the counting numbers have a geometry to them. And then it just goes on from there. So I just chose a very simple example. But as soon as you have that sort of realization that grade 1 mathematics is actually intellectually rich and profound, it'll sustain you deeply all the way through in your own personal career, as well as your career of helping youngsters on their journey of mathematics.
James, thinking about going back and exploring the mathematics at that lower level, because, I think I was that math teacher who thought there's no way I could go back and teach, grade 6 or lower, just because that mathematics, I'd be so bored out of my mind. And would I teach kids how to count? But it's only been these last couple of years where, my work with Kyle and thinking more deeply about how to best help teachers has allowed me to, explore that and find those nuances that you said, and find that great learning that I'm doing about that lower elementary. I've only just recently come to appreciate that. So I'm glad you brought that up.
And actually, too, something that jumped out at me, James, was, thinking back to, we had a big leadership conference here this past November, and we had some great speakers, including Dan Meyer and Kathy Fosno and Graham Fletcher, that were here with us to share here in Windsor, Ontario. And in Dan's keynote, he brought up this element of mathematical surprise.
Mhm.
And just like you had said, you had articulated the idea of the commutative property, and 3 times 4 and 4 times 3 results in the same 12. The same mathematical surprise that was sort of ruined for you through the Pythagorean theorem. That okay, so you had the opportunity to build these triangles, but there was no understanding. It was almost like, oh, okay, that's surprising, but let's not actually dive deeper here. I'm just like, we're just going to calculate these things that, I'm going to have you memorize to be true. And one that Dan brought up, and then Kathy Fosno actually worked into her keynote the very next day, was the mathematical surprise of like, when you add any two odd numbers, the result is always even. And like how mind-blowing that is to a young child, right? Like it doesn't take much to blow your mind. And that could be a super boring concept unless you want to actually go and look at those subtleties like you've argued and like you've articulated. So like the first, 80% of my career, I'll say, I was bored out of my mind because I was just teaching steps and procedures. But then it's been these last few years that I've really been amazed at how like beautiful it really is and how exciting math class can be when we actually sort of, really chew on an idea that might seem simple on its surface, but really unpack what's going on under there, because there is so much and it's connected to so many things as well.
And this is really interesting because I actually think K-6 mathematics is the most profound of all, because it runs into a really challenging problem that's very thorny intellectually. That we like to believe that mathematics is modeled by the real world, that we start, and we human beings, was our first mathematical activity is counting, the counting numbers. And then we extend beyond that. And as soon as you start getting to the negatives, you realize something is slightly amiss and slightly afoot. And yes, we can start putting physical models to the negative numbers. We talk about negative temperatures and debt and all the rest. But then you start to have the sense that these models we create are artifices, or they're just inadequate in some sense. They never actually get to explain why negative times negative should be positive. And we get onto these subtleties. Well, if I do the opposite of the opposite, then I'm back to the beginning. Sure, but is that really attending to why multiplication of negatives is positive? Or is that just talking about the negative being back to being positive? Is that the same issue or not? It's actually very, very thorny when you start moving from the concrete model of playing with pebbles, the actual calculus of mathematics, to a little more abstract system. And you realize all our real world models are correct to some degree, but only to some degree. And we still have this feeling that it should be speaking truth all the way through, and it doesn't, because every mathematical model actually breaks down. And it's the K through 6 world that suffers from that challenge. Well, sorry, suffers is the wrong word. That is contending with that challenge. And if it feels like mathematics is always speaking truth with what a model portrays, then that's actually going to get you into big trouble. The thing is, how do you break away from what the model seems to be saying and choosing when you want to believe certain aspects of it and when you want to let it go because it's not adequate enough? And that's a very deep intellectual step there. And it's very hard for adults to do. And I think it's unfair we expect kids to be able to handle it, to be honest. I think negative numbers are hard. Negative numbers are a high school topic, I'm sorry. So are fractions. They should be revisited all the way through K through 12 and then attended to again at university. They are
absolutely
subtle.
Yeah, we're realizing that in our district in Greater Essex. We have spent a lot of time over the past year and a half in fractions, and it's like the more you learn, the thornier it gets, to use your term. And it's interesting because what immediately jumped into my mind, and I cannot recall the author off the top of my head. Maybe John may know, but the article on like rules that expire.
Yes.
And this idea that we often tell kids things and we say it like it's 100% true, like the smallest number is 0. It's the lowest. It's as low as you can go. And then all of a sudden one day we basically break it to them that, hey, guess what, kids? I was lying because that's not true at all. And that, oh my gosh, the next number after 1 is 2. I've told you that for years. And then all of a sudden it's like, wait a second, there's actually like a number halfway between. And oh my gosh, there's another number halfway between, like 1 and 1/2 or 1 and 1 1/2. And oh my gosh, like what's happening now? And it's just like it all starts to unravel the deeper you go, which I think is what we should be sort of priding ourselves on is this whole, again, that idea of that mathematical surprise that if you keep on digging, it's like rabbit hole just keeps going and you'll never come out the other end, it seems.
So here's the big thing about anything you do in life and read and learn. It's all about context and nuance. In a certain context, yes, 0 is indeed the lowest you can go. But if you start to expand your context and your understanding, and you expand your picture, then you have to reassess where does a statement like that stand. So it's not so much that we're lying, it was just the fact that we're now asking students to expand their sense of awareness of what could be, and then context change, which then does require reassessing what you choose to believe or not believe. And we don't talk about that metacognition so much in math class, where math is actually all about that, the metacognition of what you're doing. So and this is what worries me, this public perception that, I liked math because I know when I'm right or wrong. Well, you're right or wrong in a certain context, but actually only in that context could you be deemed right or wrong. If I change context on you, then it's a different ball game. You have to reassess what you're choosing to believe. We don't have those metacognitive type discussions in the standard curriculum, and we should. And to me, that is the greatest gift that we could teach the next generation, to always stand back and reassess what you think you know and how you know it, and whether it still applies in the context you're currently aware of. And the answer could be, yep, it's still the same, fine, great. Or it could be, I'm more aware that, I could go all the way. We live in a very turbulent political system. Maybe my understanding of my family's politics is not quite adequate to understand, nation politics or global politics. It's context. Expanding context requires continual reassessment of what you think you know and how you think you know it. And I think math class is perfect for that. When all you know is the counting numbers, life has got some good stuff to it. And as soon as you start expanding it to negatives, then questions appear, and they're good questions. And it just changes your perception of what the lowest number could mean, or what even a common factor means. In fact, I was just looking at some curriculum materials in international curriculum this morning, who was asking, an exam question was asking, what's the greatest common factor of 4x cubed and 6x squared and 10x to the fifth or something like that? And obviously they wanted the answers, I can't remember what numbers I just said, but they wanted an answer like 2x cubed. That's the obvious answer they wanted. But then you realized, hang on, this is algebra class. X represents an yet to be determined value. It could be a fraction, it could be an irrational number, in which case asking for the greatest common factor of 4, the square root of 17, and 3 is meaningless. Because every number is a multiple of any other number in the real number system. So there is no highest common factor of some polynomials, except in the context, obviously, what you want to be talking about is, no, I only want to be working with polynomials with intercoefficients and integer powers of x, in which case the greatest common factor has a different meaning, blah, blah, blah. But we'll teach kids, here's how you answer that type of exam question. Actually, there's a lovely meta discussion to be had there. Technically, There is no answer to that question. It's a meaningless question. It's a silly question. There are no greatest common factors in the real number system. There's an epiphany right there. Great, fabulous fun. And then what could the examiners mean? What could the curriculum authors mean by that? And then you're trying to assess what tool they're trying to get at for what purpose. And then we'll learn about factoring polynomials down the road if we need them. I personally don't think we do, but the curriculum thinks they're a vital skill that every student. Oh well.
I can't help but when you describe that problem and your explanation, I would be first of all curious if any students would be brave enough to share that insight. If let's say they had noticed what you noticed about that particular question, if X was a fraction or these different scenarios. Yeah. It makes, to me, it makes us kind of look at math and to try to make math more like some of the social sciences from, and even just like this idea of philosophy. And I'm picturing when I wrote an essay was so creative and it was all about perspective and opinion and being able to bring in, I'm hearing some of those elements, like you're describing some of those pieces to make math a lot more like many of the other subject areas that we learn, and to give you more freedom that, it's not going to be as easy as right or wrong like it maybe was for us when we were in school. It's about, kids actually expressing some deep thought and the metacognitive piece that you've articulated so nicely here.
Mm-hmm. Also, when I think about my experience, and I've become a quite a different teacher from just a few years ago, but I was hoping when I was planning my lessons, that those questions didn't come up during my lesson. I didn't want a kid to bring that up because that would derail my lesson. That you've got this you've imagined this flow from one spot to the other, which was very procedural to get that learning goal out into the open. And I'm hoping that the kids don't bring these questions up because now we have to derail the lesson to go this way. Or maybe I didn't even know how to answer them. I'm like, and that would scare me. And I know there's a lot of teachers out there that the math sometimes scares us to go into those deeper conversations.
Yeah. What if I don't know the answer?
Well, I know. So there's definitely this fear that, or this expectation, you need to be the expert in the room. There's that feeling, and there's a parental expectation that you are. And that to me is unnecessary and sad, but actually is completely necessary in the sense that, how is mathematics success defined in the classroom? It's usually defined by the assessments that are given. And in the end, the assessments that truly matter are the big provincial or state or national exam type things, which are really about answering math facts under speed with one correct answer, by and large. So, I'm painting a very sad picture of the math curriculum to this day, but we're still stuck in that 19th century model to some degree, where math success is defined as speed answers to what questions. In which case, I will never blame a kid for wanting to garner success via the tools that best prepare you for that success, namely memorize and do. I will never blame a teacher whose definition is actually defined by student assessment success, in which case the best strategy, you could argue, is to attend to the test in a very direct way. Mm-hmm. I didn't say teach the test because that's a bit too sad, but definitely attend to it. You must attend to it, in which case it's a strong focus. And if that's the world we're in, then I do not blame one whit for operating in that world. So my thing has always been, how can I get my kids to still pass those exams? I had no choice. When I was in the system, I had no choice but to over the particular exams I was giving, but still find those moments, those baby steps, those elements of just teasing apart that sense of meta thinking, of cognition, of playing with ideas, that sense of joy. What's the mathematical thinking here? And transmuting the idea that math content is sacred, because actually I don't really care about factoring quadratics, to be honest. In fact, most quadratics don't actually factor, by the way. That's not important.
The vast majority.
But if you use it as a vehicle for teaching thinking, then sure, let's talk about quadratics. That's a great topic to teach thinking. So the content becomes the tool, but not the sacred element of the work at hand. But that takes a major mind shift, and especially when the exam in the end is all about how many of these quadratics can you factor in a hurry. What can you do? You have to factor those quadratics in a hurry. That's all you can do. It's interesting.
Well, you've kind of brought us to a really nice place here, because we did want to talk to you a little bit about, when you were teaching in the high school, you definitely, we're going to say you've got a really strong background in the mathematics. And even secondary math teachers, while many are very confident with memorization and procedures and, hey, I could complete the square of, anything you throw at me. But they might be wondering, so when you went back into the high school, like, did you have any challenges or barriers that you were up against? And some of them are structural, I'm sure, as you've mentioned, this idea that at the end of the day, you might not have been able to write your own exam. So you didn't get to decide what was going to be assessed. However, what were some of the other challenges that you experienced that may, make you more empathetic? Because I did hear you say that you don't blame the teachers for, kind of having some of these beliefs, I suppose, based on the system that we're teaching in. So what were those challenges and barriers like for you while you were in the classroom?
Let's see. So there definitely went through some cultural shocks on the mathematical level. So when I left the university world, I actually looked at K through 6 through 8 through 12, and I decided to go to high school in particular, because I felt like that was the toughest challenge of thinking about where's that wiggle room for joyous mathematical thinking, because I got the sense the culture of high school is more or less, and forgive me for speaking so bluntly here, but there's that element that, okay, all fun and games are now over. We're now in lockdown mode. Our job is to get you into college. Right. I felt like good stuff was going on in K through 6 and 6 through 8, but I felt that high school had a particular mentality to it that we're now serious. Fun and games are out. And the one thing that shocked me was how much diagrams and pictures were eschewed from the curriculum. Yes, you draw pictures of graphs, but that's it, And I think so much mathematics,
and that's only because it was on the test, right?
I think so much of mathematics is actually visual. And I'm going to be controversial here, but I think our brains, our mammalian brains, are primarily visual as well. And pictures speak 1,000 words and spawn 10,000 ideas. It shocked me that people did not realize that completing the square, despite saying the words, is actually completing the picture of a square. And the whole story of quadratics is not about solving these equations. It's really a story of symmetry. Why do we like squares? Because they're symmetrical. If I told you I had a rectangle whose area was 36, you know nothing about that rectangle. It could be 4 by 9, could be 4.5 by 8. Who knows what it is? If I add the adjective, oh, by the way, my rectangle is symmetrical, then you suddenly know everything about that rectangle. It's a 6 by 6 square. That's the power of symmetry. So really, the mathematical lesson of the quadratics unit is about the power of symmetry. It comes up in the algebra, because you can literally complete the square of these things. And it comes up in the graphing, because turns out these graphs are symmetrical U-shaped type graphs. So to graph anything, all you do is find two symmetrical points on a symmetrical U-shaped graph, and common sense tells you everything. That's the power of thinking like a mathematician. Oh, and answer all the exam questions too, by the way. So that was my delight of being a high school teacher, but also my challenge. And I was definitely a strange beast. It was very hard to talk about this, and especially amongst my immediate colleagues, because here's this guy, a PhD from Princeton, coming in, hand-selected by the heads of the school to come in and do this stuff. What's he going to think of us? I knew I was intimidating, and it turned out I couldn't really talk about teaching with my colleagues at that time. It's not since I've left that school that we can start having conversations about it. So I was doing a lot of stuff in private, and just behind my classroom door, which is always open. So open classroom door. But that was hard. So obviously, I really enjoyed taking a topic like quadratics, thinking, okay, what's the true mathematics story really going on here? What's the thinking I want to teach as a mathematician to these kids, and get them to pass those exam questions? So that was my greatest challenge. I was kind of on my own, didn't have anyone I could talk to about it. Okay, that's fine. But I kind of loved it, but I was also perturbed by that, just how closed the system, how scared the system was at the time. I think things have changed now. Whatever you think of the Common Core in the US, I will applaud it simply because it talks about understanding and thinking. The content, sure, it's got funny, quirky things in it, but it's still the same math content. That's not the issue. But as soon as you start using the words understanding and thinking, you got thumbs up from me. I'm sure it's not going to be perfect, but anything to do with those words, I'm in. Count me in.
Right. And I heard you saying about this idea that math is visual, and that just in general, like humans, we are very visual. And I always struggle when I hear people say, well, this student is not a visual learner, or this one is. And I'm going to argue that, well, like, assuming that they don't have a visual impairment, students are definitely visual, because think of how much we are seeing every single second of the day, every time we open our eyes. And math, like you said, it began in the real world. It's concrete, and then we can use visuals to help us better understand it. And then eventually we get sort of lazy, and that laziness leads us to the symbols, which is kind of funny, because I always used to sort of think that my students were the lazy ones because they didn't want to use the symbols or the operations and all this algebra, when in reality it was sort of the opposite. I was the lazy one because I was using symbols to represent something that was way more complex. And I'm wondering if if a teacher's at home right now listening, saying, "Hey, I'm a secondary teacher, a high school teacher, and how can I make sure that I help kids to see that the math is visual? What might be some approaches that pop into your mind?"
Well, I mean, one thing that always strikes me as delightfully curious is that when people realize that when you talk about the powers of x to a little superscript 2, x to a superscript 3, x to a superscript 4, we have the words for the first two of them, x squared, x cubed, and they realize that's actually geometry. We're just actually saying geometry in an algebra class. And so it is an epiphany for people that realize x squared is the area of an x by x square. And x cubed is actually the volume of an x by x cube. And then it's curious we don't have a word for x to the fourth power. Well, why is that? Because we humans aren't very good in 3 dimensions, beyond 3 dimensions. So that's a little epiphany right then and there.
Well, one that's even easier or more simplistic than that is how long I went on before I realized the idea of squaring just regular old numbers, not even x's. Right. And, that I was like, oh, like that's really what's happening. Like I knew 3 squared was 9. Yeah. I knew that because, my teacher made me know that. And I knew that I could square root 9 and get 3. But it took me a very long time, like till I was actually teaching when I was like, I could actually take like these little square tiles and I could make 3 rows and 3 columns and that was 3 squared.
And I can't do that for 6.
And I can't, it was like mind blowing. Yes, I'm like, absolutely. What is going on here?
Yeah. So my point is exactly that, is that there are clues all throughout our arithmetic and our algebra that speak geometry, and just become cognizant of them. The word square, be it, in the algebra class, or as you just said, the square numbers in arithmetic. It is actually geometry. I think so much of our mathematics is geometry. And even the square root. And what does the word root mean? Why would I say the square root of 3 is 9? And what am I asking for? I'm asking for the root feature, the foundational feature of a square of area 9. Well, that's probably its side length, is the thing I want to know about. Hence, the square root of 9 is its side length, 3, of the actual square of area 9. And then that makes you realize that people get fussy, but they won't use the square root symbol for negative answers. They won't say the square root of 9 is -3 using that square root symbol. And that's because the story is a human one, that was a symbol invented for geometry, because we're now talking about the actual physicality of actual squares, in which case you will not have a side length of -3 with the geometry. That's why we will not say in arithmetic class with that radix symbol that the square root of 9 is plus or minus 3. Now, in algebra class, if I was asked to solve x squared equals 9, then I will say x is either 3 or -3, because the context changed. We're not speaking, per se, geometry in that algebra class. But, those sorts of stories. Our human story of mathematics is actually extraordinarily visual from the get-go, and there's clues that visual story all the way from the beginning grades upwards. Square numbers being an obvious first place to start.
Yeah.
And also, I'm obsessed with the vinculum. I think the vinculum is just a gorgeous story to tell. That horizontal bar symbol, which was used in about the 1200s, 1300s to represent groupings. Sort of, do you call them brackets or parentheses in Canada? I always get confused when I go to different countries.
Interchangeable.
Yeah.
Mostly brackets.
Ontario seems to be a bracket sort of province, but I think it kind of goes back and forth depending on where you are.
Yes. So back in the 1200s, people used to put a horizontal bar. If I wanted 2 + 3 + 4, and I wanted you to think 2 + 3 first, please, and then go +4. We put parentheses or brackets around the 2 and 3 these days, but they used to put just a horizontal bar on top of the 2 and the 3, saying, I want 2 and 3 to be the first thing that comes into your mind, and then add 4. Great. But, that notation went out the window with the invention of the printing press, because vinculum was very hard to print in the half-line positions. So they decided to go with parentheses that could have tiles that stayed in the same line, and we're stuck with parentheses now. But it's actually fabulous to look where the vinculum still survives in mathematics today. Whenever you see a horizontal bar, it usually means grouping of some kind. When I write an infinite repeating decimal as 0.18 with a bar above the 1 and 8, I'm saying that 1 and 8 are being grouped together, please, to be repeated. Even the square root symbol, we think it's one symbol, like a little hook symbol with a bar. Actually, that's 2 symbols. That's a radix, the hook, and the vinculum, the bar, because people got confused when I wrote the square root of 4 + 6. Did I mean the square root of 4 and then add 6? Or did I mean the square root of 10? So I put a bar with the square root sign to make it very clear what they were grouping. A little visual clue right there. And of course,
I just learned something.
Yeah. That's due for me, for sure. Yeah. I didn't know that about the grouping.
Then go to algebra class. When kids see 2x + 4 all over 2, it's very tempting to cross out that first 2 from the 2x and that 2 on the bottom and not divide the 4 by 2. But you realize, oh my gosh, there's a vinculum there. It's a bar. So that 2x + 4 in the numerator is all one group. All of it gets divided by 2, not just part of it, all of it. So the story of the vinculum there is telling me, 2x + 4 is the entire group. So divide it by 2, please. X + 2 is the answer. So, there's all those beautiful visual clues throughout the story of mathematics that pervade up to algebra class even and help with common algebra problems.
like we just said, like my mind is just exploding. And that actually, now that I say that, it makes me think about exploding dots. And I know that when I say James Tanton to another teacher, they're like, "Oh, that guy who's doing exploding dots." And I wonder if we can shift to talk about that a little bit. And if anyone who's listening who doesn't know about exploding dots, can you fill us in on like where that came from? What made you think about that? Like what's involved with exploding dots?
Oh my goodness. Okay, so I mean, here's one of the most beautiful and profound stories of mathematics. It really is the invention of how we write numbers with place value. The story of place value is actually profound. And exploding dots is something I had been thinking about just before I actually started teaching in the high school world. I was thinking about these ideas of when I was doing PD work with teachers. I was actually thinking about polynomials. I thought, why do we have to teach polynomials? What is it about polynomials that a high school student should care about? And it's really, I realized polynomials are just numbers base x rather than base 10. If you think of it that way, then everything you do with polynomials is comes to repeat in grade 5. And that made me realize, okay, there's a true story here. It's the power of place value in its own right. So when I went into high school teaching, I really developed this storyline, which I called exploding dots, of trying to bring a visual image and the power of visuals to the story of place value. So I guess the idea is the Asian cultures have it right. I think they've got a visual image of mathematics in their brains early on as youngsters with the abacus. An abacus is just a bunch of rods with beads on them. And the idea is you slide 10 beads to the top. And so you get 10 beads to the top, bring them down and move one bead up, one rod over. So an abacus is actually representing base 10. So I've just done basically take the idea of an abacus, but not be locked into base 10, be locked into any base you like, and just draw dots that explode, because who doesn't love explosions? As soon as you've got 10 dots in a box, kaboom, they disappear and are replaced by one dot, one place to the left. So it's a visual and immediately appealing way to see, to play with the mechanics of place value until you have an epiphany to realize, oh, this Tanton guy is playing with place value. When he puts 273 dots into a machine and gets the code 273, we are really talking 270, that TY being short for 10, and 3. Suddenly we have internalized the idea that we do speak in terms of powers of 10, and the mechanics is very visually obvious, these ideas of exploding dots. And then the lovely thing about that is you can just keep playing with it. You're not locked into 10ness. We humans are obsessed with the number 10 on matters of arithmetic and counting because of our physiology. Though you realize there were some cultures that were base 20, probably because they were aware of their toes. There's some cultures that were base 12. In fact, a lot of Southeast Asia is base 12 because there's a very natural way to count to 12 on one hand. You think about using it.
And bakers.
And
right?
Sorry? And bakers.
Right?
Well,
12,
and then,
base
but
12.
yes, well, heck, everything's human. Why do we in trades and measure go with 12 a lot? Bakers and 12 inches in a foot and so forth. Because 10 is a very awkward number with very common fractions that come up in everyday life. I can do half of 10, fine. Mm-hmm. But often you want to deal with quarters and thirds of things. Awkward for the number 10. 12 is a much more natural number when it comes to matters of basic fractions, half, thirds, and quarters. Hence, you want a dozen of something. Because if I only want half a dozen or a third of a dozen, I've got a good whole number of loaves of bread, which is great. So there's a human story there. But then, once you realize that you're just playing with place value, exploding dots makes all these school algorithms of long addition, long subtraction, long multiplication, long division obvious, just visually obvious. Just do it. There's nothing to understand. You just do it, and there it is. And then just do it again in some unknown base. And just to make algebra teachers happy, let's call it base x. And then suddenly you realize all of high school polynomial algebra is just a repeat of grade 5, and no one told you. No one told you. So I would do this in my high school classes that are meant to be teaching factoring of polynomials, all this stuff. Well, I'll spend a lesson going through base 2, base 3, base 10, going through all high school, all of grade school arithmetic again. But suddenly, as soon as you really own that for the first time in your life, and I think you've got maturity by your teen years to really start to own that, then polynomial algebra, which I'm meant to teach for 2 weeks, is trivial. There's nothing to do. So we had like 2 weeks up our sleeves to play with. So it was great. Right. But then what pleases me as a mathematician, the thing about mathematics, there is no such thing as being done with a topic, because every answered question invites more questions. So why stick with finite polynomials? And then suddenly you can do infinite series with these exploding dots. And lo and behold, we're doing some, infinite series and calculus type stuff. Great, all is obvious and straightforward. Geometric series formula, piece of cake with these exploding dots. But why stop there? I'm working with like 10 one machines where 10 dots explode, one box become one dot, one place over. Why not get quirky and start mixing up the numbers? And you can discover things like base 1.5 and base phi, the golden ratio, and base this and that. And suddenly you're in unsolved research territory. So this one story of just looking at an abacus and just thinking deeply about an abacus, in about an hour, you can go from knowing nothing and learning how to write numbers for the first time, whip all the way through the grade school arithmetic, whip all the way through high school polynomial algebra, do some elements of calculus with infinite series, and get to some unsolved research questions, still challenging mathematicians to this day, all within an hour or so, just through playing with the incredible visuals of these dots.
Yeah, when I first came across, your work around exploding dots, again, the explosion happened to my mind, and I had shared it out with some teachers in my district, and we had kids in our district in primary playing with the 2-to-1 machine and all the way to the 10-to-1 machine. And, they're starting to add and do all kinds of craziness with it. And then we had kids in high school, like you said, who zipped through all of that stuff. And they were sort of in a way, almost like, what is this? This is so easy. Yes. And then you all of a sudden open the next door and it's like, oh my gosh, I'm able to operate on polynomials and I'm able to, do all kinds of crazy things with this one mathematical model. And I think, John and I always say that the work we spend on the conceptual understanding, like the underpinning of how all of this stuff in mathematics works, even though like teachers are constantly struggling to find time, it's always like time is such an issue. I think the reason we run into that is because we teach everything so siloed and so separate that we don't actually see the connection. So like you had said, if you spend a little bit of time here, you're unpacking this mathematical model, as Kathy Fosno would say, like a power tool that you can go back to and continue extending instead of introducing this new idea that's completely brand new, completely foreign to everything that I've known previously. And instead, I'm building on top of it. And like you said, you had oodles of time left. Like that's what we find when, we're working with concrete manipulatives and different visual models. And, I want to thank you for obviously unpacking that for me, because it was one of those things. I had a minor in computer science. I understood binary. And when I started playing with the machine and how long it took me to go, oh, wait a second, this is binary? Oh, and oh my gosh, it all works the same. Oh my goodness. It's right there before your eyes. It's, it's a great way for kids to problem solve and like build their critical thinking skills while also developing a conceptual understanding of just how numbers work. And that to me, I think is just magical. If that's all kids take with them, is just this idea that I know that everything in mathematics, it all has a reason and it's all interconnected some way, somehow. I might not understand them all yet, but I know that it's possible if I was to, dig at something deep enough.
And that's one thing I really do wish to bring to the curriculum is that sense of story. It really is a story that does go from K through 6, through 8, through 12, through 16 and beyond. It's a beautiful human experience. And, let's share that with our fabulous next generation. Let's bring that story to the world.
I just, Kyle was just talking about like that power tool and stretching it from, one side of the grade to the other. And I really appreciate when you said that high school algebra was really just a repeat of grade 5. And that brought to my mind another power tool that not until recently became something that I also saw that we were doing in grades 4 and 5 that we could put to use in high school algebra, which is the area model. And I know that you are a big proponent of the area model for doing various things like algebra and also multiplying, say, 2-digit by 2-digit numbers. But we've also seen that the exploding dots model can also be used for like multiplying 2-digit by 2-digit numbers. What would you say to a teacher who's wondering about, like, do I use the area model, or do I use exploding dots, or do I use one first, or do I do one second, or do I do both? Is there a progression that you'd recommend is optimal? Like, what do we help these teachers kind of answer these questions?
Well, okay, so that's a good question. So okay, one thing is not to be locked into a literal way of thinking. That okay, so I am having people draw boxes and dots when they want to divide big polynomials, but in no way would you want to, every single time you divide two polynomials, draw a whole bunch of dots and boxes. It just takes too long. I'm not saying that we must do it this way. You'll find after a while that if you actually do want to divide a lot of polynomials, you'll stop drawing the dots. You'll just write the numbers instead of dots, and you'll stop drawing boxes after a while. And then you realize you have like a little shorthand for yourself because you've got the visual first in your head. And what you're doing is on paper is just a rough representation of that visuals in your head. It's not meant to be the actual literal visuals anymore. So when I say do exploding dots, I don't say please don't make your kids draw dots every single time or just drive any sane person bonkers. I'm not saying that. Let them make their choice. And one thing you'll realize after a while is that exploding dots is a model and it has its limitations. Yes, you can multiply polynomials just fine in it, but it's a little bit tedious. Division is actually extraordinarily simple and slick, which is amazing. But multiplication is actually not quite as nice and slick. And you'll realize that the area model actually is a much more sort of clean way to do polynomial multiplication. I would say do it all, do it both, and just pick and choose as you go along. Right. Basically, and again, don't bother drawing the actual areas of rectangles every single time. Once you've got the visual in your head, that's all you need. If you want to draw the rectangle, great. Exactly. If you don't, great. All is good. As long as you can figure out how to articulate what you've done to someone else if they ask you about it, that's all you have to be able to do. But definitely oscillate back and forth and give a sense of empowerment to students to pick and choose. So when I did teach exploding dots in my classroom for polynomial division, I also did the area model because isn't it great to be able to see the same thing from multiple different perspectives and it all comes together beautifully. Now go ahead and pick and choose which way you like.
Beautiful.
And this is one thing that really saddens me. As I mentioned earlier, I am looking at one particular international curriculum right now, and I'm seeing the exam questions are such that, please solve this question via this method. And as soon as they say that, it just makes my heart sink. Isn't it better to just say, please solve this question and be able to justify how you got there? It's a much more empowering question.
Right. And maybe articulate why you picked that particular strategy, you don't have to evaluate that, but just out of curiosity, like, why did you think that, completing the square here was a better idea than going at it graphically or going at, whatever strategy. It's interesting because I've heard you throughout this discussion talking about the visual and talking about mathematics. Like, I'm hearing this sort of, I'll call it concreteness fading or CRA approach, or, recently a colleague of mine shared the idea of an acronym called ELPS, which I guess was in Great Britain, for some time, this idea of like, in math, like thinking experiential first and then building the language in and then building the pictorial and then the symbolic. But regardless of what you want to call it, it's just this, it seems like this idea that if we are working in an abstract land mathematically, that symbolic land, I liked how, I was picturing in my mind, the dots turning into the numerical symbols and then the boxes and exploding dots sort of fading away. And then all of a sudden, you sort of have yourself a bit of a standard algorithm created, or at least a algorithm. It might not be standard, but it is an algorithm that works. And the beauty is that you could always go backwards. Like what I see when I'm thinking about concreteness fading, this idea of me in my mind being able to, if I got stuck, I forgot a step, I forgot, how to get there. It's like driving in my car and the road is closed. I'm not stuck. I don't just get out of the car and call an emergency vehicle to come pick me up. I take a different route. And this allows you to kind of backtrack. It's like you understand the mathematical terrain conceptually of how this concept, came to be. And you always have that to fall back on if you're more, we'll call it efficient or more, less cumbersome way of getting there ever causes you any
Yeah,
problems,
or
right?
just-
If you forget along the way, you always know how
You've
to
got
get
something
back.
to hold on to. Something to hold on to. Memorization. If I forget how the pluses and minuses go in the quadratic formula, I'm doomed. But if I understand, I can always just draw a quick square on the side and do it that way and figure it out, then you're good. You're golden.
Right. How do you go ahead and try to dive deeper into an idea, like go more abstract, like deeper down that complexity? If all I'm doing is sort of like building off of rules that I've memorized, which were built off of other rules, which were built off of other rules, but I never really understood how that first rule came to be, right? Like that's a pretty
Yes.
insecure. Yeah, that foundation is pretty wobbly, right?
Right. So that's the thing. So the real question is to penetrate through the huge pages and pages of stuff and ask, what's really going on here? What's the actual core of this idea that makes it tick, that makes it work? And if you can find that, then you can always build off of that at any stage of your life and revisit it multiple times in your life to see it in new lights, new contexts, new nuances. It's that really what is the core? And like I said, for example, to me, quadratics, the story of quadratics is the story of the power of symmetry. As soon as you've got symmetry in your life, then you can use it to your fabulous advantage. And look at the algebra quadratics, look at the graphing quadratics. The teaching that sort of thing is just, I think, is actually a life lesson, to be honest. It's not so much being caught up in the details. Of course, you have to attend to the details, but be able to step back and say, what is the thrust of what's really going on here? That's a life skill. That's a major life skill.
And to think about that visualness again, it really okay, I guess the word is irks. It irks me when we view visual tools or concrete tools as some teachers might call them, like lower or a crutch, and only use tiles or counters or pictures or diagrams if you need it, and not and because you can't do the abstract algebra. It really bugs me when teachers say that or push for that. Like, you have to go to this way and we want you to go there right away. And if you can't do that, you're not operating at a higher level.
I know, and that operates everywhere. I mean, it always struck me as odd that we teach kids the long division algorithm first, in the sense that, what I mean by that was an algorithm that was actually devised after many, many, many decades, if not centuries, of process. I mean, ink was special. Ink was precious in the 1700s. So you wanted to write something on paper that used the least amount of ink as possible. So we came up with all these algorithms for arithmetic that were very compact and very short and strange. So the long division algorithm we came up with is the end of a human process of trying to understand what the process is and then compactifying it to use as least amount of ink on precious paper. But then what do we teach kids first in the old curriculum is, here's the long division algorithm, the end of a human process, not what led to that process in the first place. I have nothing against teaching the long division algorithm, but if it's done without thinking, then I have to argue what's the point, because any right-minded human will get out their smartphone to actually work out 276 divided by 12. That's the smart thing to do.
Right.
However,
or just ask Siri to do it for you.
Whatever. Exactly. That's what you would do in this day and age. So if you're not teaching without thinking, then don't teach it at all. But I do say teach it, but teach the thinking, because there's a lovely story there that led mankind from knowing what division was and figuring out this beautiful way to write it on a piece of paper that was kind of compact and neat. Now, turns out you're right that it really is exploding dots. Just you got lazier and lazier and lazier, and I don't mean lazy, but like more efficient. You didn't need to draw the dots. You wrote numbers. You didn't need to draw the boxes. You just drew lines, or didn't bother drawing the lines anymore. Or you just wrote some staggered table of numbers. Voila. You know what? It will look like the standard long division algorithm, very much so by the end of it. That's a wonderful human process. And to be able to step back from that and see that is a lovely meta lesson for one and all. So let's teach the meta lessons too.
Yep. No, I love it. I love it. And I know for me that one of my greatest challenges, even after I realized that, we should be teaching for thinking, was I realized, wow, I've got a lot of work to do because I don't understand the story of long division, or I don't understand the story of quadratics, or, despite the fact that I could do all the formulas, I could do all the algorithms. And I think the big message that I want to make sure that people are hearing from this conversation is that's okay. There's no shame in that. It's just, but the work has to be done, and we can all do this together. And that's really what this podcast is all about.
And you know what? It's actually joyous. It's actually joyous, fabulous work. It doesn't matter what level you're at and where you feel like you should be. There's no get rid of the word should. You just at where you're at and just go for it and do so with joy and bring others along the way with you.
Absolutely.
Great lesson.
Well, listen, James, we don't want to take up too much more of your time. This has been a fabulous conversation. So we have one last question for you, and it's really it's going to be open for you because we want to know from you, like, what is your current professional learning goal or focus for this particular school year? Like, what are you working towards? What's on your mind?
Well, okay, so I really don't believe that we need content in our life so much in terms of think of what teaching has been in the last 2 centuries about how to do this, how to do that, all about content. But we live in such a content-dense, content-rich environment right now. It is so easy to find out how to solve a quadratic equation. Just Google it. In fact, Google is fabulous. So we live in a 21st century where content is no longer the goal. It really is understanding process and assessing what you know, how you know it, and try to identify what you don't know and how you might go about finding it out. And I think what we really need to start thinking about and focusing on this in this 21st century's world is teaching the art of asking meaningful questions. Now, it's easy to ask, I don't get it type questions and clarification questions. They're good, fine too. But what are questions that help you probe to a deeper level of understanding? Like I've got a sense there's something there about quadratics. I just don't quite get what they're about. The word quad, that means number 4. Why are the number 4 when these equations about x squareds with number 2 in them? So how do you teach the art of wanting to ask questions and then figuring out how to ask meaningful questions? So what's going on in my mind now is really what I and my family and some colleagues are doing is trying to think about how do you teach the art of asking meaningful questions? Because I think that is the skill of the 21st century and beyond. And it really comes down to what I was saying earlier. How do you assess what you think you know and how you know it? If we could just give that to the next generations, what a powerful world we could be living in. You see a problem in your life, be it, something to do with the schooling, or be it, why is it that girls aren't able to go to school in my village? Or, why can't we have clean water? If there's some problem, you feel like you have a sense of agency, that you can take some first steps to ask a question and make some steps towards getting towards some sort of answer, any kind, any type of step is the duty of us for the next century or two. So, yes. So I'm thinking obviously math curriculum. I'm trying to think about these questions in the math curriculum context. But I think I'm also in my brain, I and my family are really working hard on teaching the world the art of asking meaningful, productive questions. And how can we do that at scale in a way that brings joy and success and agency to one and all? That little thing. That's what we're working on right now.
Awesome. Huge ideas. You got an undertaking there for sure. Well, there you have it from James Tanton, who is clearly a lifelong learner. So we want to pose the same question to you listening at home. Like, what is your big professional learning focus going to be for this coming school year or to finish out this year? Consider writing it down and pausing this right now and setting yourself some checkpoints to monitor how you're working towards achieving that goal.
Alongside Exploding Dots, James is also working on building the Global Math Project. And he's been tinkering with some new software as well, I know. And he didn't mention it here, but I've had a chance to check it out, called Beagle Learning. We're going to make sure to put all the links in the show notes. I know for Exploding Dots, explodingdots.org works for you. Global Math Project, I believe, globalmathproject.org or .com, but we will put that in the show notes, as well as the Beagle Learning link. Tons and tons going on there. Obviously, this is all under the umbrella of those big ideas that James just shared. So we'd love to hear about your responses and your reflections on social media at Make Math Moments. And on the episode show notes page, you can also put some comments, makemathmoments.com/episode 6, or even through email. Never hesitate to reach out to us. So James, John, and I want to thank you so much for joining us on the Make Math Moments podcast. And hopefully we'll be able to get you back on the show before too long to hear what new projects you're working on, including your Global Math Project, how Beagle Learning's shaping up, and what other projects you have on the go at the time. I'm sure there will be others.
Well, gentlemen, the real honor's actually been mine. What you guys are doing is just tremendous and fabulous. So congratulations to you, and keep it up. And multiple thumbs up and full support from my end. You guys are just tremendous and awesome. So thank you for all you're doing here. Honored to be on this podcast with you.
Thank you. Thank you so much.
Thanks, James. We will catch you soon, my friend. Thank you again, and have yourself an amazing day.
You too. Thanks so much.
Thank you for listening in on this discussion with James Tanton. One of my big takeaways from this was when James confirms the fact that all levels of math are wonderful, deep, and intellectually rich. I think some of us need reminders of that. There's so much we can do to dive in right in our own grade levels.
My big takeaway from this conversation was around the letting go of the expectation that we have to be experts or the experts in the room. We often put pressure on ourselves to know everything and anything about mathematics, but unfortunately, I'm guessing that many of us can relate to James' experience in school where he was taught rules and procedures over understanding. And if that's the case for you, then we can't beat ourselves up. For me, hearing that come from James makes me pause to remind myself that it's going to take me time, a ton of effort, and patience to build up all of that understanding that I missed along my own K through 12 math journey. So thank you to James for that reminder.
Just as a reminder, if you want to join us on the podcast for an upcoming Math Mentoring Moment episode, where we have a conversation with a member of the Making Math Moments That Matter community, like you, who is working through a challenge, and together we will brainstorm ideas and next steps to help overcome it. You can apply over on makemathmoments.com/mentor. That's makemathmoments.com/mentor.
We want to thank our sponsor, Whitebook, for this episode. If you've listened to past episodes, then you know that both John and I regularly have our students solving problems while standing in groups at the whiteboards. For the last year, we've been using Whitebook's flip charts as the writable surface. We love that these dry erase boards have one side blank and on the other side has a grid. And we love how portable they are. You can easily put up the boards on the wall with tape and change your mind to move them around. For us, we bring them on the road when we're doing workshops. They're great for all of these purposes. So as listeners of this podcast, Whitebook has given you a special deal. You can get the Teacher Starter Pack, which includes a variety of great teacher stuff for your classroom. Check that out at mathmoments.whitebook.ca if you're in Canada. And if you're shipping anywhere else in the world, head over to mathmoments.whitebook.com.
In order to ensure you don't miss out on new episodes of this podcast as they come out each week, be sure to subscribe on your favorite podcast platform by simply searching or use these quick links. For iTunes, go to makemathmoments.com/iTunes.
For Google Play, go to makemathmoments.com/play.
For Spotify, go to makemathmoments.com/Spotify.
And quick links will work for most other popular podcasting platforms as well. We have to thank you so far for all of the subscribes we've been receiving. We've been in iTunes top 200 education podcasts for the last couple weeks. All of those subscribes and those reviews help us reach a wider audience. So be sure to hit subscribe and give us a review. Also, you can tweet us at MakeMathMoments on Twitter. Show notes and links to resources from this episode can be found at makemathmoments.com/episode 6. Again, that's makemathmoments.com/episode 6.
You can also find Make Math Moments on all social media platforms and seek out our free private Facebook group, recently named to Math Moment Makers, K-12. Don't miss our next episode where we'll be engaging in a math mentoring moment call with Sarah Jane Wells from Toronto, Ontario, Canada. This was a super powerful conversation where she shares how realizing her personal privilege has affected her teaching habits, how she's been working on sparking curiosity consistently to get kids engaged and keep them on task. And a big can of worms was opened when the conversation moved into assessment, evaluation, and the role of descriptive feedback. Get ready, because that's going to be a great episode.
I'm really looking forward to that episode. But if you're not interested in waiting until then, why not watch our 4-part series on building resilient problem solvers who don't want to stop learning math when the bell rings? You can find that free 4-lesson video series at makemathmoments.com/lesson1. That's makemathmoments.com/lesson1. Well, until next time, I'm Kyle Pierce.
And I'm John Orr.
High fives for us.
And high fives for you.